Hi everyone. So today we're going to continue on 11.1. So what I want to do is go over the problem from last video, which is this one right here. Y double prime plus 2y prime plus y equal to 0 with y of 0 equal to 1 and y prime of 0 equal to 0. So show you how that is done. So once again, it's pretty straightforward. So this is my differential equation. So what I'm going to do is rewrite that into differential operator form. And then I can write it into my characteristic equation. Notice that this one would factor into r plus 1 squared equal to 0, and therefore r equal to negative 1. Notice that that is a repeated root. We have the same root twice. And the tricky part is that you don't use the same exact e to rx twice, because they would be linearly dependent and therefore doesn't form the proper dimension. Remember, this is a second order differential equation. Therefore, its solution must be a two-dimension subspace. Okay, so it can't have just one root. So what is this solution? So based on theorem 11.1.1, that would say that our solution y would equal to c1 e to negative x plus c2 x e to negative x. So that's our general solution. So now let's try to solve for our particular solution. So let's go for it. So let's say, before I do that, I'm going to go and do this. I'm going to go and do y prime, because I do need that for this initial condition. Now, y prime is a little tricky because of the following. So negative c1 e to negative x plus, notice this is x e to negative x. That means that when we differentiate this, we'll have to use product rule for that. So make sure you don't forget. So therefore it becomes C2, 1d2, so negative x e to negative x, plus 2d1, which is just e to negative x. I could clean this up a little bit, but I'm going to just leave it the way it is for now. And I'm going to just go and plug into my initial condition. So y of 0 equal to 1, tell me that that would equal to 1 equal to c1 plus c2. E to 0 and x, just c1 plus 0 c2. Because if you plug in 0, you have e to 0 plus c2 0 e to 0. So that actually go away to 0. So therefore, we know c1 equal to 1 directly, which is pretty good. Okay, and so now what I'm going to do next would be the following. So now we're just going to do the second initial condition, which is y prime of 0 equal to 0. So therefore meaning 0 equal to negative c1 e to the 0 plus c2 negative 0 e to 0 plus e to the 0. So notice this go away to 0. And this is 1, so therefore just become 0 equal to negative 1 plus, this is 1, so 1 times c2 is c2. So therefore tell me that c2 equal to 1 also. So that's pretty easy. And once again, it is nice because we're using 0 as the initial value. So therefore our solution, y, would actually equal to c1, which is 1, e to negative x, plus c2, which is 1, x e to negative x. So that become my answers. Pretty simple. All right. So I'll give you another one to try before I show you a different type of questions I want you to be able to do. So here is same thing, just a very basic differential equation. 2y double prime minus y equal to 0 with y of 0 equal to 1 and y prime of 0 equal to 0. So very similar to what we just did. I think the initial condition are the same, but obviously the differential equation is a little different. All right. So how should we proceed? Well, we'll proceed the same way. So that would be 2d squared minus 1 of y equal to 0. Note that this is just y, so therefore it's 1, not d. Okay. And then that just basically come out to be 2r squared minus 1 equal to 0. That would be our characteristic equation. Now notice that this one is actually not factorable because of the 2. And I can still do the following. I can be careful, is that I'm going to move the 1 over, divide it by 2, and then take the square root. But remember, when you take the square root, it becomes plus or minus 1 over radical 2. Or you can think of it as R1 equal to 1 over radical 2, and R2 equal to negative 1 over radical 2. Or if you rationalize it, you can say you can say radical 2 over 2 if you want to. But if not, I'm okay with 1 over radical 2. It's not a big deal. All right. Good so far. So now notice that the root in this case are irrational, but it doesn't change the way we form our solution. Our solution still maintained to be the same. Y would equal to C1 e to the 1 over radical 2x plus C2 e to negative 1 over radical 2x. Okay? And now it's just a matter of solving for the solution. So now this one does require me to take the derivative again to form the first derivative for the initial condition. So I'm going to do that. So therefore that becomes 1 over radical 2 C1 e to 1 over radical 2x minus 1 over radical 2 C2 e to negative 1 over radical 2x. Now, of course, this type of problem will be a little more complicated due to the fact that we have the radical, which will make it a little harder to deal with the coefficient, but maybe it won't make me a big deal. Hopefully we will see. So I'm going to start with y of 0 equal to 1. So that, by now you should see that's equal to 1 equal to basically C1 plus C2, because both of these e would go away. And that gives us a first equation. Y prime of 0 equal to 0 would basically tell me that 0 equal to 1 over radical 2 C1 minus 1 over radical 2 C2. Notice that this second equation is interesting because I can actually just cancel out 1 over radical 2, and that will have C1 minus C2 equal to 0, which imply C1 must equal to C2 for that to work. And with that being said, that would mean that 1 equal to C1 plus C2, or then just become 1 equal to 2 C1. And therefore tell me C1, which is equal to C2, which is equal to 1 half. So now I have my solution. Y equal to 1 half e to the 1 over radical 2x plus 1 half e to the negative 1 over radical 2x. That become my differential equation solution. All right, so that's the solution to this differential equation, initial value problem. So now the next thing I want to show you is this. We can actually use the fact that because we know the way the solution, how the solution of this type of equation work, we can actually reverse engineer the problem if we kind of know what the question, what the answer is supposed to look like. So give you a new type of problem to work with. So suppose I ask you for the following: find a differential equation such that y equal to e to negative 2x plus 3 e to 5x is a solution. So the way it works is the following. In this case, notice that we are given a specific solution and we try to find out what question would give us this solution. So the idea is to first realize that this solution is basically what we call a particular solution or a specific solution subject to the initial condition. So this is a specific solution subject to some kind of given initial condition already. That's the reason why it doesn't have C1 and C2, but instead have actually a coefficient in front. Seems to me that this solution has two different terms, e to the negative 2x and e to the 5x. The tricky part is we actually don't know if there are other terms or not. And you might be thinking like, well, obviously we know because that's, we don't see them. But the problem here is that we don't know if we have other term that might have a 0 coefficient in front because of the initial condition. So we can only assume that one possible solution to this, a general solution, would be this. Oops. So this is a possible general solution. Oops. General solution. And make sure you understand is that why is this just a possible general solution, but we don't know actually if it is a general solution, because we could have other term where the C just so happen in this specific solution, they become 0. So here we can assume that this is our general solution. So therefore, that would tell me that y equal to e to negative 2x plus 3 e to 5x are just basically y equal to c1 e to negative 2x plus c2 e to 5x with c1 equal to 1 and c2 equal to 3. And we could have more term with just the rest of the c becomes 0, which is possible. So therefore, when we generate this solution, this equation that could have this function as a solution, we don't know exactly if that is the solution. It would be a possible solution, equation that would do that. So now how do we actually do that? So notice that the general solution is spin, or actually maybe I'll write it this way, has a basis e to negative 2x and e to 5x. So therefore, since I know these two terms are solution to a differential equation, therefore indicate that it should have two characteristic roots at the very least. Could have more, it could, but we don't know. But we do know at least they have two. Okay, so what are the two characteristic roots? I'm going to say call R1 equal to negative 2 and R2 equal to 5. And therefore indicate that R1 plus 2 would have to equal to 0, and R2 minus 5 would have to equal to 0. Or actually, maybe I would say just R and R, because then that would generate R1, this would generate R2, and therefore now I can reverse engineer my characteristic equation. So that becomes my characteristic equation. From the two characteristic roots. Now, is it the only characteristic equation that can generate this solution? Once again, no, because it could have more term, and then the solution that we're given just have a whole bunch of coefficient becomes 0. That's all. But we do know that the characteristic equation must have this part in it. So therefore now I can say, well, that would mean if I multiply this out, that's r squared minus 3r minus 10 equal to 0. So that is our characteristic equation. Therefore, form d squared minus 3d minus 10 of y equal to 0. And now I'm ready to write my differential equation, which is y double prime minus 3y prime minus 10y equal to 0. So this is a possible equation that our given expression, this, will have to be a solution of. Now, if you're not sure, we can definitely check. So we can do a quick check just to see that our solution will satisfy it. So e to the negative 2x plus 3 e to 5x. So to plug it in, I do need y prime, which is negative 2 e to negative 2x plus 15 e to 5x. And now let's do y double prime. So y double prime would equal to 4 e to negative 2x plus 75 e to 5x. So now the question is, would these three things plug into my differential equation? Would it satisfy it? So let's find out. So that would be y double prime minus 3y prime minus 10y equal to 0. So therefore, we 4e to the negative 2x plus 75e to the 5x minus 3 times this will become plus 6e to the negative 2x minus 45e to the 5x. Minus 10 times that will become minus 10e to the negative 2x minus 30 e to the 5x. And notice that that do come out to be 0 when you kind of count the terms. So here's my e to the negative 2x, e to the negative 2x. And then these are my e to the 5x. And therefore, it does come out to be 0 equal to 0. There you go. It's checked out. Okay, so notice that this allows us to actually try to write the equation based on a given solution. Now, do understand is the following. We actually don't know if the equation that has this as a solution could be a higher degree than 2. And as I say, just simply because they could have just a whole bunch of 0 coefficient for the rest of the term. So we don't know that. So therefore, this is only one possible equation. This equation would definitely have this, possibly have this as a solution. But this is not the only equation that would do that. So make sure you understand that, and that way you don't, get confused. Now, let me give you another example to try out. Okay. And how about this one? Find a differential equation. Differential equation. That has the following expression, y equal to, how about 3e to the 2x minus x e to the negative 3x. That has this as one of its solutions. All right. So the process basically works out exactly the same. So what you want to do is try to identify the roots, the characteristic roots, and then use that to help you kind of figure out what the equation would be. Okay. So in this case, the tricky part obviously would be the x e to the negative 3x. Because of the fact that you have an extra x in front, that basically indicates that we have a repeated root. So in this scenario right here, we can imagine our solution would be this one. So this one actually would be something like this. Technically speaking, is basically we have something like this. Because of the fact they have an x, it automatically meaning that it has to have something like this. A term where there's just a single negative 3 as a root. In this case, basically this solution basically would mean that we have C1 equal to 3, C2 equal to 0, and C3 equal to negative 1. Notice that even though that doesn't have this term, it doesn't mean that it doesn't exist in the general form. That's the problem. And as I always said, it could also have a whole bunch of other terms which have all the coefficient equal to 0 also. So, but we're not going to know what they are, so we can't account for them. So we can only do is to say that that might potentially be other term, therefore meaning that our equation potentially could have to be higher degree. But right now, I think based on what we're given, we can assume that our equation is maybe 3rd degrees, but could be higher than 3rd degrees. So what we're going to do is try to write out a 3rd degree equation at the very least. So to do that, notice that this gives me R1 equal to 2. This gives me R2 equal to negative 3. And this is a repeated root, therefore R3 equal to negative 3 also. Negative 3 also. So now I can say, well, because of that, that means our characteristic equation should be R minus 2, R plus 3, R plus 3. So now it's just a matter of multiply this out and then try to write out our differential equation. So if I multiply this out, I can say R minus 2, these two multiply to R squared plus 6R plus 9. And then when I multiply this in, become R to the 3rd. minus 2r squared plus 6r squared minus 12r plus 9r minus 18. So therefore, if I combine like term, that will be r to the third minus or plus 4r squared minus 3r minus 18 equal to 0. So therefore, now I'm ready for my differential equation, which would be y triple prime plus 4y prime, y double prime minus 3y prime minus 18, don't forget the y, equal to 0. So that would be my differential equation, and this would have that as a solution. Now I could ask you to verify it, but actually that would be quite a lot of work because you do have to take this to the third derivative for this thing right here, and this part requires product rule every single time. So I'm probably not going to ask you to do something like that, but just be mindful that I could, if it doesn't have the repeated root, I could definitely ask you to just take the derivative and plug it in and check to make sure it works. All right, I think that's it for this video. So we'll finish up 11.1 in tomorrow's video. All right, talk to you guys later. Bye-bye.